everyone, and welcome to the exercise 4 on basic mathematics. While the last two exercises were more about how to build the optimization problem, this week we finally actually gonna find some optimal solutions. The first task is to consider the objective function f of x. We have two design variables, x1 and x2. In the design space, x is from -8, x1 is from 0 to 10, and x2 is from -8 to 8. And we see the function f of x plotted here. In the first task, we have to calculate the stationary points. So basically find the candidates for our optimal solutions. Then we check the nature. So if they're minima, maxima, or saddle points. Then we got a little in-between exercise, how to determine the definiteness of a non-diagonal matrix. And then we add a equality constraint to this problem, which is that the solution has to be in a plane that is somewhere here defined by x1 is equals to 1. And so we have a constraint optimization problem now. And we're gonna solve this, and those are necessary conditions. So finally we have to check if the sufficient conditions are actually met for this boundary optima that we computed in task 4. Calculate the stationary points. We have f of x is x1 minus 2 times x1 minus 5 times x1 minus 7 plus x2 squared. So we build the gradient, which is the gradient for the first component of the gradient is the partial derivative of f with respect to x1. So it's x1 minus 5 times x1 minus 7 plus x1 minus 2 times x1 minus 7 plus x1 minus 2 times x1 minus 5. And the second component is df with respect to x2, which is simply 2x2. And if we multiply those components, we got x1 3 times x1 to the power of 2 minus all the mixed terms, 28x1 plus the last terms, which is 59, and here we still got 2x2, and we know that that has to be equal to 0. So we know that our optimal point x is simply the solution. Well, both terms have to be 0, so this is just solving the quadratic equations, which I'm sure you all know. Over to a, and here we got 0. So here we got plus and minus, and therefore we got two optimal candidates, so two stationary points, x1 star, which is 3.21 and 0, and x2 star, which is 6.12 and 0. Now we have to check the nature of the stationary points, so we compute the Hessian, which is and evaluated at the stationary points. The Hessian is simply the second order derivative, so component-wise it's d square f over dx1 squared, and at the stationary point, and here we got over dx2 and then over dx1 and x star. Here we got over dx1 and over dx2 and x star. And finally here we got, we differentiate twice with x2. If we do that, we get 6x1 minus 28. Here we have 0, here we have 0, and here we have 2. So here you can always check if those two off-diagonal elements are the same, because by the definition of the Hessian, those two have to be the same, because of course this is the derivation is well, you can change the order of the derivation and you still should get the same solution. So if you don't have the same elements, maybe check. Okay, now we evaluate our Hessian at x1 star, and we have, well, minus 8.740, and here we got 2. And since this is a diagonal matrix, we can, it's sufficient to just look at the diagonal elements because they are the eigenvalues, and we can look at the signs to determine if the definiteness. So here we see they have different, the two elements have different signs, so it's indefinite. Our Hessian is indefinite, and therefore x1 star is a saddle point. H of x2 star is 8.72, 0, 0, 2. Here we got two positive eigenvalues, so our Hessian is positive, definite, and x2 star is a minimum. Okay, so here we have a diagonal matrix, so we can check the signs of the diagonal elements. If that's not the case, we need different methods to check the definiteness or the definiteness of our Hessians, and therefore the nature of our stationary points. We have two, well, we have more than two, but we'll try two different methods. First, we try to, well, we're going to compute the eigenvalues. The general eigenproblem for the Hessian is h times v is lambda v. So we compute the eigenvalues by setting the determinant of the eigenproblem to 0. So for h of x1 star, we compute the determinant of H minus lambda I. This is the identity matrix. Here we got 1, 1, and 2 minus lambda. And this is the determinant, so this times this minus this times this has to be 0. And this is again just a quadratic equation. That's 18.48. So we have lambda 1 is minus 8.83 and lambda 2 is 2.09. And note that usually they are ordered according to their magnitude, to their size. So we start with the smallest and then go bigger. So not magnitude, but just order them from the smallest to the biggest. Okay, they have different signs. So x1 star is, our Hessian is indefinite. So as before, x1 star is a saddle point. And for h of x2 star, we have 8.72 minus lambda, minus 1, minus 1, and 2 minus lambda. So that's lambda squared, again this times this, minus this times this. So we got lambda squared minus 10.72 lambda plus this minus this is 16.44 equals 0. And the two eigenvalues, lambda 1 is 1.85 and lambda 2 is 8.87. So our Hessian is positive, definite, and x2 star is a minimum. There is another way to check the definiteness of the two non-diagonal matrices, which is using the leading principal minus. We get those by building the determinants of the Hessians by just crossing out lines and columns. So for a 2 by 2 matrix, we have to check the determinant of H11 and the determinant of the whole matrix. Okay. You have to be a bit careful here because you can only use this to check for minima, so for positive definiteness. This is usually not a big problem in the optimization because optimization problems are mostly formulated as minimization problems, or in other cases you can just reformulate it. But yeah, just keep it in mind. Okay. For h of x1 star, we have the determinant of h11, it's just that component. And then we have to build the determinant. Which is this times this minus this times this. We've done that before. It's minus 18.48. So since they are not both positive, we can't say from this what x1 actually is. Then from x2 star, 16.44. So here both are positive. So our matrix is positive definite. And x2 star is a minimum. For the fourth task, we have to calculate the extremum, but now we add a equality constraint here, this plane, this gray plane at x1 equals 1. And to calculate the extremum, we start with the Lagrangian function. Which is L of x1 and x2 and also lambda f of x plus lambda times h of x. And in case you're wondering, this lambda has nothing to do with the eigenvalues of before. Lambda is just a very popular letter. And here it's a Lagrange multiplier, if you know that. And it's used to enforce the equality constraint. So we have f plus lambda times h. To compute the extremum, we use the KKT conditions, which is dl over dx1 and dl over dx2, and thirdly dl over d lambda. So dl over dx1 is the derivative of f with respect to x1, and then plus the derivative of lambda times h with respect to x1, which is lambda in this case, and that has to be 0. And dl over dx2 is still only 2x2, and that has to be 0 as well. And dl over d lambda is just the equality constraint, so x1 minus 1, and that has to be 0 as well. Now we got 3 equations for our 3 unknown variables. So we have x1 equals 1, x2 equals 0, and we can plug that in here and get lambda equals minus 34. So our extremum here is x star at 1, 0, and also lambda star equals minus 34. The Karushko-Tucker conditions are just necessary for boundary optimas, so we have to check the sufficient conditions for the boundary optima. The sufficient conditions are defined that, well, the KKT conditions have to be fulfilled, which you already did, but additionally the second order derivative of the Lagrangian function at our optimal solution, which is d square L over d x squared, has to be positive definite on t of x star. And t of x star is our tangent subspace, which is defined by the vectors d, and they have to be unequal to 0. And in case when we just have equality constraint by dh over dx times d. Has to be 0, so the dot products. So D has to be orthogonal on the subspace, and also by the active inequality constraints, but we don't have those here. What we want to do with this is basically we know now that there is it's a minimum on this plane that we defined by the equality constraint. But we also want to know if it's actually a minimum on this plane, so on this tangent subspace. In this case, the tangent subspace is just made up, well, by all of x2. So it's enough if we check L x2, x2, because x1 is constrained by the equality constraint, and that's 2. So 2 is larger than 0 for all x star, because it's always a constant, but sometimes you have to plug that in here as well. So we know it's a minimum on the tangent subspace. Why do we have to make it so complicated? Just one word. So we've shown that the sufficient conditions are fulfilled as well. We're done. Just one word on why we have to make it so complicated and can't just check the Hessian like we do for interior optima. If we remember the Hessian from before, it was something like so if we go, if we evaluated that x1 star, it's actually minus 22 and 2. So the matrix at x star, the Hessian, is actually indefinite. And also we've seen it before, indefinite, that x1 star is actually a saddle point. But for the constraint optimization problem that we wanted to solve here, it's a minimum, so it's the optimal solution for the constraint problem. In the second task, we have to solve an engineering problem, find the optimal length A and height h to maximize the volume V of this container. We have a given surface area and we have a force Fa that's kind of pushing from the side, and we don't want the container to tip over. In the first task, we have to define the optimization problem, reduce the problem dimension with the equality constraint, and then we have to formulate the general problem statement, so solve the optimization problem. Okay, name the design variables. Well, the design variables x is we want to find the optimal length A and also the height h. The objective function is f of A and h. Is we want to maximize the volume, so minimize the negative volume. And the volume here is simply A squared times A, so that's the base surface, and that's extended into the third direction, h. The constraints. we got an equality constraint because we have a given surface A of h of A and h is S, and S has to be equal than the surface, so we got the base and also 4 times the sides has to be 0. And then we got an inequality constraint because we don't want it to tip over. And for those of you who are interested, this equation comes from a moment balance. So we want kind of the moment that's created by that force. We need F1 to be as big to for that not to tip over. Okay, so it has to be F1 has to be bigger such that the moment created by FA isn't larger than FA times this, and mg, we got this. Okay, so we get an equation like FA times h halves minus mga over 2, and that has to be smaller or equal than 0. Also, we got a constraint on the design space because we know that A and H have to be larger or equal than 0 because they are physical quantities, and we don't have upper bounds, so they can go until infinity. Okay. Reduce the problem dimension explicitly with the equality constraint. So we use our equality constraint. A of A and H, H of A and H, which is the surface area. And we solve that for the height H. Over 4A, and then we plug it into the objective function, which now has the only design variable A because we eliminated H. Okay, and one A cancels out here. And we do the same for the inequality constraint. And we still got a constraint on A. And now we just got one design variable left. Okay, now we can write down the general problem statement of the reduced problem. We got f of A is minus A s minus A squared over 4. We want to minimize f of A. Subject to g of A is fa s minus A squared over 8A minus mga over 2, smaller or equal than 0, and A has to be between 0 and infinity. And finally we can write down the Lagrangian function. L is f of a plus mu g of a. So here we use mu instead of lambda because we have an inequality constraint. Is and the rest is just copying the formulas. Okay. Now we want to solve the optimization problem. So we build the partial derivatives of the Lagrangian. Let's write down our Lagrangian once more. So first let's build the partial derivatives with respect to our design variable and also with respect to mu. So that would be the case when the inequality constraint is active. So here we got s plus 3/4 of a squared plus mu times fa times minus s over 8 minus 1/8 minus m times g over 2, and that has to be 0, and that's basically g of a, and that's h, and that has to be 0. So we can compute a from this equation. So that's the square root of fa times s over fa plus 4mg, which is 1 meter, because the other solution to this square root is -1, and that's out of the design space because the design space only starts at 0. And then we can use that to compute mu, which is minus 6.3 times 10 to the minus 4, and that's square meters per Newton, and that's smaller than 0. So we know we were actually not correct, that this for the optimal solution the inequality constraint is active. Just to see it later, we can compute f of a here. That would be minus 1.25 meter to the power of 3. So now we can set mu to 0 because we know that the constraint is inactive. So we only left with dl over dA for mu equals to 0, so that's plus 3/4 times h squared. So we know that h can solve that for h, and this is now the optimal solution, square root of 2, and our f of h star is minus square root of 2, and that's our optimum. Now we solved our reduced problem, but we still have to compute the optimal height, h star. So we just plug it into the equation, and we got 1 over square root of 2. Now we're back to our familiar 3-bar truss problem that we studied extensively in I think it was the first exercise. What did it look like? We had 3 bars with 3 different cross sections where those 2 were the same, and we had forces here which was also the same, and we wanted to find optimal cross-sectional areas A1 and A2 star to minimize the mask while not exceeding the strengths of the material, which was also determined by the material properties. Now we changed this problem a little bit. We know that the exercise in this exercise, bar 2, is manufactured of a less sturdy alloy, so our sigma yield is only 140 megapascal. Before it was 216, I think. We also know that now we got our solution. We got our optimal solution at a point where G2 is also active. We see that here in our plot, so this is the direction of decreasing mass, and our optimal solution for A1 and A2 will lay here at this intersection of G1 and G2. In the first task, we have to compute the gradient of the objective function at A star. We have to determine the active constraint functions and their gradient as well. Then we have to show that this solution that we have given here is actually the optimal solution. And finally, we got 2 little Matlab exercises. Okay, let's start to compute the analytical gradient of the objective function at A star, and we know that this won't be 0 since we have active constraints. So we have f of A star, it's given here again, it's rho times L times 2 square root of 2A1 plus A2, that was our mass for the whole 3-bar truss. And we know that dF over dA1 is 2 square root of 2 times rho times L, and dF over dA2 is rho times L. And we can plug in the values we know. So we get 22.34 times 10 to the power of minus 3 kilograms per square millimeters. And here is 7.9. And that's the first task. Now we have to determine all active constraint functions and calculate their gradient. We have given that G1, or we know that G1 and G2 are actually active. How can we check if that's correct? Well, we just computed. So we got the constraint, which is the absolute value of sigma minus sigma yield has to be smaller or equal than 0. That's also given on the last slide. And so that's our sigma 1, 1. So the stress in the first bar with respect to the first force here, minus 260 megapascal, which is sigma yield of the first bar or the first material. And then we can plug in the values. And that's our Optima A2. And that's a 3. And minus 216. And it's actually 0. So we've shown that G1 is active at A star, so at our optimal solution. If we do the same for G2, we see that it's also 0, and for G3 it's not 0. It's actually minus 150 megapascal, so it's smaller than 0. So we've also shown that G3 is inactive. Now we have to compute the gradients, and it's kind of a pain. So for G1 over A1, we derived this with A1, well, without the stars. And then we'll plug in the values again, so our optimal values, and also the value for F. And we get a formula something like if you have fun at that kind of stuff, you can also make this term more simpler. But for our use case here, it's sufficient to just have something and we can plug in the values. And for G1 over A2, we have minus F times and that's minus 0.092. And then we got the gradient for G2 over A1, so we take G2, which is sigma 2, 1 minus sigma 2 yields, or 140 megapascal, and we derive that with A1 and finally we do that with G2. Okay. Yeah. Now we have to use the Karushko-Tucker conditions to show the optimality of the solution. So the KKT in general are gradient of F plus gradient of G transposed times in a vector product, in a matrix vector product with mu has to be 0. We also know that G has to be smaller or equal than 0, that mu transpose times T has to be 0, and also mu has to be larger or equal than 0. So we've shown in the last task that G1 and G2 were 0. So we know by that our mu3 is 0. We know that mu3 is 0. And now the only thing we have to show is that mu is at A star is bigger or equal to 0. We've also shown in the last task that G1 and G2 were 0 and G3 was smaller than 0. So we're good there. And to show that our mu's are larger than 0, we use this first equation, that the gradient of the Lagrange function has to be 0 at A star. So we have df over dA1, and we have df over dA2. And here we have dG1 over dA1 and dG1 over dA2. And then we have dG2 over dA1 and dG2 over dA2. And we got the same for G3. And this times mu1, mu2, mu3 has to be equal to 0. But we know that mu3 is 0, so we can cross out that column and that line. And then we're left with two equations for two unknowns, and we can invert this matrix, and we have all the values because we computed them in the last task. G1 or dG1 with respect to dA1 was minus 0.35. This was minus 0.092. Here we had minus 0.13 and minus 0.18. And we have to compute the inverse of this times the gradients of f. That's what we computed in the first task. And that was and also for A2. So mu1 and mu2 are 0.059 and 0.0139, and this is in kilograms per megapascal. So also the mu's are larger than 0. We've checked that. So the Karushko-Tecker conditions are fulfilled, which was the condition for A star to be the necessary condition for A star to be an optimum. And we can also look at the geometric interpretation. If you remembered, we had G3 here, G1 here, and then we had a G2, which was somehow here. So we got A1 and A3, and here we have A2. This is G3, this is G1, and this is G2. That's basically the plot from before. We have our lines of decreasing gradient, so that's minus gradient f. And now we look at our optimal solution here, and we have our gradient of G1, which is G1, so the gradient is orthogonal here, and we have our gradient with respect to G2, G1 and G2, and this together gives us our minus, oops, yeah, we don't need that one. So that's gradient of G1, and that's gradient G2, and so the resulting one is minus gradient f. So the gradient f shows in the other direction, and that's the geometrical interpretation, or basically sketch, and therefore we've shown that f is actually also an optimum since the sufficient conditions are satisfied. So f is convex, and A1 star, A2 star is an optimum. Since f is convex, so the KKT conditions are also sufficient. Okay, so now we compute the numerical gradients using the Matlab script. First, there's some problem setup. The analytical functions are given again, just to illustrate later, to do the plots. Then we got our objective function, we got our two active constraint functions, and then the to-do starts. So for the 3.4 we have to use the forward finite differences to approximate the gradient, use a step size of 0.5 and no noise, and we also have to implement the finite difference function. Okay, so the method we want to use is FFD, forward finite difference, and let's jump to line 153. There we go. There's also the central finite difference, which we used, I think it was last task, and the backward finite differences, so you can play around with that a little bit if you want to. The forward finite difference is you take one value that is from xi, the objective function at xi plus delta xi minus the objective function at xi over delta xi. So the gradient with respect to x1 is the output function. So that's what we've given here. We got a method, we got the output function, so something like f or g also, and we got delta x, our step size. We got the two values x1 and x2, so the optimal values for a1 and a2 given here, because that's the point where we want to compute the gradients. Okay, so output function of x1 plus delta x, and we keep x2 fixed, minus output function of x1 and x2, and then over delta x. For the approximate gradient with respect to x2, we got basically the same, just that we keep x1 fixed and change x2. Now the sample in this case is x1 plus delta x and x1. Okay. Then we go back to our to-do. Which curve we want? We want to compute the approximate gradient of m, g1 and g2. So the gradients the analytical gradients we computed in the first task. So that's curves. Curves is, as we see here, a struct with name value pairs of the three functions, and we want all three of them for the first task, so for 3.4, sorry. Okay. Step size, we use 0.5, we have that given here, and no noise. Okay. Let's run it. And we got our graph here. So that's G2 and that's G1, and our optimal solution is here at this intersection, somewhere, and we compute the gradient of G1, G2 and also M, that's those iso lines here, at this point. Okay, the values we got from the approximate gradient are given here, and if we compare them with our analytical values, we see that they are pretty close
So it's not exactly the same if you look at the later digits here, but it's not that bad. You can also play around with different step sizes and different methods to see when the gradients become worse or better. Now for 3.5, we add some noise to the input data. So now we got the input data for G1, maybe from measurements or something. So we add some noise to curve values, curves of 2-point value. So that's G1 here. And we leave the step size. And then let's look at what the gradient, the approximate gradient does. Curves. Okay, so now this is our approximate gradient. And we see that it's supposed to be a gradient for this function at this point. So it's really, really wrong. Why does this happen? If we zoom in a little bit, we got some noise. So just here it's simulated using some sine function that's added on top. And then we use those 2 points here indicated by the stars to compute the gradient. And since that's somewhere in the sine, the gradient comes out really, really wrong. How can we mitigate this change? So how can we make this gradient more aligned to this function? So actually closer to the real gradient. Gradient of the real function if we wouldn't have the noise. Well, we see here that we got this problem because those 2 points are really close to each other and they are somewhere in the sine. And the sine is something, so noise is just on top of the real function, but with a very small amplitude usually. So we just have to pick a bigger step size, so we kind of smooth over the noise. Okay? So let's change to something like 50. And then you see we got different points here. They are really far apart, kind of. But the gradient looks much better. Also here you can try different step sizes and also use different gradient approximations. But the key is always to filter out the noise. The key is always to make the step size bigger. You shouldn't make it too big because then it becomes, well, kind of wrong again. Or let's say inaccurate. Wrong is the wrong word. It becomes too coarse. So more inaccurate because you only want to smooth over the noise. You don't want to smooth over the whole function. And that's actually it for this Matlab exercise. So let's go to the next task.
Okay, the last task is on calculus of variations. We have again a little engineering problem. We want to find the optimal distribution R of xi, so the radius over this variable xi along this bar to minimize the deflection U of L for a constraint mass M. So it's basically the same engineering problem to the example you heard in the lecture. Just now we have a circular cross-section and not a rectangular cross-section. we got our objective function, which is the mass, which is the deflection u. We got the constraint function, which is the mass, has to be m0, and we can build the Lagrangian function from this, or functional, which is f of r plus lambda times h of r. Okay. How do we find the optimal distribution? Well, we got our Lagrangian. Our Lagrangian is f of r of xi plus lambda times h of r of xi. And we want to build the delta L, which is basically delta f plus lambda times delta h. So first we compute delta f, which, as you remember from the lecture, is something like a generalization of a partial derivative. So we have we introduce those arbitrary test functions phi of xi and we have delta f is the limit of epsilon going to 0 of d over the epsilon of f of r of xi plus epsilon times v of xi. So we go step by step. At first, we just use f, which we have given on the last slide, and plug in instead of r in the integral, we just use r plus epsilon times v. dxc. Okay, this is, now we build the derivative with respect to epsilon, and we can pull that out because it's just a constant. We leave the limit. We still got the integral. We still got the first term. This xi becomes to the power of 5 because we built the derivative. And then we got here minus 4 from here, and also the v of xi from the chain rule, so deriving this by epsilon. So we got times minus 4 times v of xi dxi, and I think now I've got a bracket too much. Perfect. And then we build the limit. So we got minus 16 here. We can take the minus 4 out of the integral from 0 to L. And then we got L minus xi squared over r of xi plus over r of xi and that's to the power of 5 times v of xi, because epsilon is set to 0, dxi. That's delta f. So it looks really complicated, but just going step by step, it really isn't. We do the same for delta h. So we have limit. So delta H is the limit of epsilon to 0 d over the epsilon of H of R of xi plus epsilon V of xi. We can use the same arbitrary test function here because, well, it's an arbitrary test function. And we end up with 0 to L to rho p times R of xi times V of xi d xi. Okay. To rho p, yeah. Now we can find the optimal distribution. We can build delta L, which is delta F plus lambda delta H. So here it is, I can take the, I can combine the two integrals. So I have the stuff from the delta F term plus the stuff from the delta H term times lambda. And then times V of xi d xi. And I know that this has to be 0 for all V of xi. And if we want this to be 0 for all V of xi, because remember it's an arbitrary test function, this integral can only always be 0 if the sum of those two components is 0. So we know that lambda times rho times p squared, I can take that on the other side, times e times r, now we got another r as well, to the power of 6 is 8f L minus c squared. So R of xi is some constant c times L minus xi to the power of to the power of 1/3, so it's the third root. Okay, we still haven't used that h has to be 0, so our equality constraint has to be actually fulfilled. And we can use that to compute our constant c, because now we know what r looks like. So we can plug that in. And now we can actually build this integral, so we can integrate this function. And zero. So building the integral of this is to the power of 5/3. So we pull it out, so we got minus 3/5 times rho times p times c squared, because we got a minus from here as well. And then we have L minus xi to the power of 5/3, and we have to integrate it from 0 to L minus M0 equals 0. So building this derivative, that cancels. Here we got minus and then L, so that's plus. Take that on the other side. We have C equals to the square root of 5/3 times M0 over rho P L to the power of 5/3. And finally we get our R of Xi, which is C times this. So let's write it down. Yeah, 5/3 times M0 over rho P L times L minus Xi to the power of 1/3. Perfect. So now we computed our optimal distribution, R of Xi, so the radius over the whole length, which is a function of Xi. And this will minimize the deflection for a certain mass. And we've seen that the calculus of variation is very powerful. And well, it's a bit more complicated than before, but really nothing to be afraid of. I hope I've shown you that. That's the end of exercise 4. If you have any questions, you can use the forum on Moodle, and maybe other students have already found the answer of what you're looking for, or otherwise I'll check it regularly and answer some questions. Yeah, I hope you understood most of what I've said, and this was my last exercise for this semester, so see you all at the exam.